our company is involved, or we develop a system for shape measurement of reflective surfaces using a technique that is not very well known, which is called deflectometry. So deflectometry is something that you experience in everyday life experience. You see on the left image a phenomenon you can see in any town, and it's very well known. And when you see this, without knowing it, you make some, or you use deflectometry. And it has long been recognized that as a very nice technique for qualitative inspection of surface defects. You may know that in all automotive car plants, manufacturing plants, the final step is aspect control and defects control, and the car goes through some kind of tunnel with neon tubes, and the operators look at the defects that can be seen by inspecting the reflected image of the neons over the car body. And we have turned this technique to really quantitative use, simply by replacing the neon tubes by a display monitor that will project fringes, and using very simple physics based on optics. It's simply using the law of reflection, Snell's law of reflections. Our product is a system that can measure various reflective parts. I will show some examples later. And it is very simple. You see that there is simply a measurement head, an object holder, and a display screen. And what is important is that you will not see any fine screw or any mechanical arrangement to align anything. You will simply locate your different elements on your tabletop. It can be used on a regular desk tabletop, and the software will take into account everything. The advantages of deflectometry is that it is basically insensitive to vibrations. I will not go into the details, but it's due to the fact that deflectometry is sensitive to slopes, and slopes are not affected by vibrations. So there is no need of any damped optical table. You can use a regular office desk to make the measurements. As compared to interferometry, deflectometry enables absolute measurement of the shape of the reflected part, and also its location in space. As you have seen, the hardware is very simple. There is only a camera, a display screen, and that's all. So it's for biblic simplicity. So this allows to make a really rugged device. And we have experienced many times putting the system in a luggage to take in the plane to go to some exhibition at Photonics West or in Japan or in China. And simply we unpack, when we arrive, we unpack the system, and it's ready to make nanometric level measurements on the exhibition booth without having to tune or to recalibrate anything. Another advantage of the deflectometry is, and it's probably one of the best advantage, freeforms can be measured with no need of any accessory, because you have not the limitations of interferometry. You can have large deviations to simple shapes. It's no problem to measure. So very nice. But actually, if it were so simple, you would see deflectometers everywhere in any optical shop testing. The problem is it's geometric. It's based on ray optics, so it's a geometric measurement, and it is extremely sensitive to the accuracy of the underlying geometrical model, namely the ray trajectories that depend on the camera lens aberrations, the display screen shape and location in space, and also the location in space of the object to measure. And when I mean extremely sensitive, it is really extremely sensitive. You cannot achieve anything if your model has not been properly identified. And so our know-how, specific know-how, is to have developed a calibration procedure of unprecedented accuracy to allow some measurements with accuracy within 10 nanometers RMS. And we do not depend on any in our system, we do not depend on any high quality mechanical or optical elements. For example, the camera and lens are simple industry grade equipment available from any kind of manufacturer. So everything is based on what is called, or what can be called the digital twin, because all the measurement configuration is modeled numerically, and as compared to systems that you may know, other metrological systems like interferometry or others, this allows to make the fine-tuning virtually. I mean, instead of having to align parts using fine screws on XYZ translation stages or gimbal mounts, that requires really experience from the operator. All the alignments are performed numerically. In other terms, the system adapts itself to the reality and not the reverse. Or you can also say it is every time self-calibrating. The measurement is fast, typically 3 minutes. And so the operator does not need to be skilled, so it can be anyone from the workshop. So time saved and money saved. So I will go to some results simply to show what the technique is capable of. First, it's a simple measurement of a spherical concave mirror. And you see the deviation, every time we present the results as the deviation to the nominal shape. So what you see is the deviation to the nominal shape, so deviation to the best sphere. And there are 4 different measurements to show the typical repeatability. And with the RMS standard deviation, so our RMS, 10, 10, 10, and 9 nanometers. And for this measurement, we have also a comparison with interferometry that shows a deviation of 8 nanometers. But more interesting, I will show, and more typical also, 3 measurements on the 3 mirrors of TMA, a 3-mirror elastic mat, simply because all 3 mirrors are freeforms. And some of concave are some are convex, and the sizes are in the typically around 90 to 100 millimeters in diameter. And for these parts, we were lucky enough to be able to have partners that could measure the same mirrors with other machines, other equipment. A nanomephos from DUI and a lithoscan from Ametec. And we have the deviation to the nominal shape, with this here an RMS value of 48 nanometers, and the other techniques give a quite higher deviation to the nominal. I will make some comments afterwards about that. I will show the second mirror of the TMA. It's a 45 millimeters convex mirror. You see, for example, the deviation from a sphere is 280 microns, so it's a real freeform. And once again, we have a deviation to the nominal that is really close. So now for this mirror, all three equipments are really very close. And finally, the third mirror, which is a 100 millimeter concave mirror. The deviation from a sphere is still around 200 microns. Deflectometry for this mirror, surprisingly, gives a deviation to the nominal much lower than the two others that seems to agree together. And so this illustrates the problems that is faced by users. Sometimes they really scratch their heads when they have different measuring techniques. They cannot explain what could be the discrepancies. And we are faced also to this problematic. It would be probably unlikely that our systematic errors would compensate exactly errors that are inherent to the part. So it's probably likely that we are closer to the good results than the other equipments. But I will not say much more about that. So as a conclusion, simply this technique, which is, so once again, not well known, and many people confuse deflectometry and reflectometry. And in our exhibitions, we are many times to explain what deflectometry is, even to senior optical engineers. And it brings the ability to do optical metrology with unprecedented easiness and cost efficiency. And so we are looking for a large part to measure. By the way, in terms of diameter that we can measure, unfortunately, the answer to this question is not is not unequivocal, because the size of parts we can measure depends also on the curvature. Concave parts, we can measure large concave parts with the system you have seen. We have seen the picture. We have already measured 800 millimeters wide mirrors for the aerospace industry. And so we are to increase our knowledge and to have more use cases. We are looking for challenging parts to measure. And also we are looking for partners for developing in situ measuring solutions, because as the technique is really very insensitive to vibrations, it is very, very interesting to integrate in situ measurement. And of course, we have, with all the information we had on the part, we are developing stitching algorithms. Also, very important from the end user is the connection with the user mechanical frame of reference for an axisymmetrical parts. And also today we are restricted to really reflective surfaces. So if we have a lens, for example, transparent lens, we have to frustrate the back reflection. But we may have the possibility to also deal with this problematic of measuring the surface of transparent parts. Okay, thank you for your attention. I am ready for some questions, if any.